Hello, hello. Good afternoon, everybody. It turns out in a week we have a midterm, and I did not realize we are 2 classes behind. I thought I was 1 class behind because I spent 2 classes doing math at the beginning. But I don't know what happened to 1 class. So anyway, so whatever we're going to be covering today, up to today, that's going to be in your first midterm. Okay. And next class, we're going to do review. So your midterm, all questions are going to be multiple choice, but to answer some question, you need to do math. And your answer may be given in terms of just equation, not in terms of numbers, okay? So make sure to practice of moving things around and writing answer in terms of variable, not just in terms of numbers, okay? So keep that in mind. So here is one example, for example. So last time we did this for the upward, and I think we got answer something like this. If I remember correctly. Okay, so when we have this answer, this tension can be found for any value of acceleration. If it is accelerating larger, there is larger tension on the rope. So if acceleration gets really large, it may snap, it may break because tension becomes really large, right? So that kind of makes sense. So can you find the answer something like that? Not just in terms of number, but in terms of something like this. So for example, answer may be given something like this in the choice, okay? To get this, you need to do a little math, 2 or 3 steps, okay? So expect that kind of thing. So they're gonna be about 1/3 question gonna be about math and 2/3 gonna be the concept, okay? So you have seen similar questions in the class. For example, math, we've been doing math, so that's how it's gonna look like. And conceptual question, you have seen clicker questions. That's how that's gonna look like, okay? It may not be same, but it's gonna be similar and related, okay? So if I'm preparing for the midterm, what would I do? I'll go through all these slides, the notes, and make sure I understand why that is the answer, how the problem is done, and so on, okay? Not just read through that and learn to do that problem, but learn to do that kind of problem. And then to check if you really learn, go to the worksheets and do the problems and questions there, answer them. If you can do them, most likely you are ready for the midterm. If you cannot, if you get too much stuck, then you have to come back and look these lectures, note, okay? Go through them again on that particular section, relearn and do it, okay? So that's how I would be preparing or checking if I'm ready or not. Okay, so that's how the midterm gonna be, and it's gonna be given on Canvas, and it's gonna be live through the Zoom. So that means you're gonna be turning on your video. You need to, okay. So if your computer does not have camera, you can use your phone, log into the Zoom using your phone, and also using the computer. So through the computer, share the screen, through the Zoom, turn on the video, okay? And make sure you are logged into the Zoom using your UCD account, okay? UCD account. When you sign into the Zoom, there is an option that says use SSO account. When you do that, it asks you to enter the domain name, where you enter UC Denver and then there is already .zoom, something like that, okay? So UC Denver, and once you go there, it's gonna let you sign in using your UC Denver email and password. So that's how you should log in, okay? And there should be your first name and last name nicely visible in the Zoom window, okay? So I see most of you just fine, okay? So
will you adjust our time for the DRS people?
yes, that will be adjusted, and you'll see in your screen you are getting more time than the regular persons. Yes, regular.
Okay.
Yes. So anything about midterm?
Sorry, just to verify, did you say that we're activating our cameras and we're sharing our screens simultaneously?
Yes.
Okay.
I think I'll also write email, sharing screen, and camera on. Taking test on Canvas. Log into the Zoom using UC Denver email, not your private account, okay?
And will this midterm still be out of 30 questions, like you said at the beginning?
Most likely 30, but I haven't made question. And looks like I'm not covering whatever material I was planning to cover. Could be a little less, but yes, you'll know, okay? But there will be enough time for you guys to finish the question though, okay? What I do is I do the test and, you know, like do 3 times more time for you guys. So for example, if I finish that in half an hour, I give you guys 1.5 hours.
Dr. Ngana, I had some questions in SI, and it seems like they're kind of being asked through the chat too. They're just asking how the equation sheet will be available to them is really the question that was being asked.
Oh, right there in the browser, you can click and open the equation sheet, okay?
Can't we just print it up and have it on our desk while we're taking the test?
If you are planning to use that way, then your camera should be showing your desk workspace.
Okay, so you see what we're looking at.
Right.
Okay, that's fair enough.
I don't want you to be browsing through your notes, okay?
Okay.
I know most of you don't, but happens, okay?
So I guess my one question is that I just would like to point out that I don't think we can all share our screens at the same time, but I'm sure that's something you guys have thought of. So thank you.
Yeah, you can, and I know you can, okay? So I'll be checking if everybody is sharing a screen, turning on camera or not. If not, I'm gonna call right away, okay?
So oh, sorry, Diana, go ahead.
If we were to use like scratch paper, because you said that there's equations, so is that why, is everybody gonna share like the desk then, since we'll be working through problems?
Oh, that's a good point. So if you are using scratch paper, so most of these questions you don't need a scratch paper, okay? So that's going to be a problem there when you use scratch paper. But I'll know what you are doing. So maybe I'll ask you to show your decks at the beginning. And if there is just a scratch paper, then I would know you will be just using the scratch paper. Okay.
Dr. Dungana, sorry. You're gonna kind of go over these rules again before the test starts, right?
I'll be sending an email during this
Okay.
weekend. Okay.
So the test will be instead of lecture day.
Yes, at the same date, time. Okay. Yes. In a week, exactly.
Should we just privately chat you our questions instead of like unmuting ourselves, or how do you want us like ask questions?
Yeah, chat. I'll be monitoring chat on that day. Yes. Okay. So should we move on? So I asked you guys to do this. So did you guys do it? Do you have equation like this for this? Can you tell me what that equation gonna be?
Well,
What's
if
gonna
it's
be?
in the downward position, then it should be minus A, right?
I don't know, but
Yes,
I'm writing it.
I say if you're gonna say it moves with the downward acceleration, that it'll be G minus A. Yeah.
Okay, so I wrote it. Let's see what other things, what they have found. Let's check that, right? Folks?
I got the same thing.
G minus A. Okay.
Yep.
Did you do that on the paper? Did you find the equation on the paper? Has anybody written that equation on the paper?
Yes.
And can share in the camera so that something like this? I don't know if I told you guys, I like seeing you guys' face, okay? So if possible, keep yourself visible. Okay, we see Kristen, let's see. Oh, so you wrote the equation, that's great. But did you also write, how did you find it? That's what I like to see, okay? The equation, free body diagram, has anybody done that?
No.
So, nobody wrote the equation and got that answer? Really? Okay, do it now then. I'll be asking maybe same question in the test. What would you do? Okay, draw free body diagram, write down the Newton's second law, just like we did last time. Show your work with this answer, final answer, okay? Once you have that, show us on the camera.
This is what I did. I don't know if you can see that.
Yeah, can you move your paper a little higher? Oh, it's in your screen.
Yeah, can you see it?
You need to do the share screen.
Oh.
Oh, hold on. I think I need to do something here before you can share it. So let me unshare it first. Okay.
Oh, it's actually just on my iPad.
Oh. So you are not signed in through the iPad?
No, I'm writing on it. Never mind, it's okay.
Oh, you can just hold your iPad. Probably we can see it.
Teresa, just do what you did at the beginning. That's what Dr. Dungan is asking. Just put it up to the screen again. Sorry about that.
I just rearranged the equation. I didn't solve for the answer yet. That's why. But I'll solve for the math right now.
You don't need to write down the number. I just need equation.
Can you see it?
Okay, yeah, that's what I'm looking for. And very first, I'm seeing T is m minus a. What is that?
Oh wait, no, just ignore that. There you go.
Okay.
Sorry.
Tension is force. Mass is not force. Acceleration is not force. So apple and oranges don't go together, right?
Oops.
Okay. So yes, can you show me? Looks like other seems good. Show me again.
So, what I did?
Okay, so T plus mg. Yeah, you are doing that algebra all the way. You did not learn the way we talked about, right? But seems like you are showing the work, and that looks good. Okay, so would be easier to see your steps if you follow the algebraic rule I asked you guys to learn at the beginning. Okay, I'm not saying your method is wrong, but that's kind of a bit hard to follow. So before I can write this equation, I need to choose axis. So let's say if I choose positive y up, then my tension is positive, mg is negative. That's the sum of forces, okay? And then mass times acceleration. Now acceleration is a, but it's down. We chose up as a positive, but acceleration is down. It's accelerating downward. Okay, downward means it's going to be negative a. So negative m times a. So now that's going to be this equation after that. Okay, my Newton's second law is this, and now I'm writing these things based on the Newton's second law. Now I'll just move this negative mg to the other side. So this being negative, other side it becomes positive mg, and I'm just copying negative ma. So that's that. So now let's say if I were to factor that m out, I get g minus a there. Okay. Little algebra there. So now why writing this way is fun? So there could be answer, let's say 1050. We'll know the answer, a number, but it's not going to tell us more than that. Now, let's look at the advantage of writing this way. Let's take a look. It's saying this g is acceleration due to gravity, and we also call acceleration a free fall, right? What if our acceleration of downward acceleration was same as g? What would happen? First, let's not look at the equation. If the elevator is in free fall, what that means?
There's no tension.
There is no tension. Tension is zero, right? Somehow the rope got snapped, broken, right? So that's what happens. Now, let's look at mathematically. When I plug in a equal to g here, this becomes g minus g, which is 0. So it's telling me tension is 0. Means you are in free fall. You see that? So tension depends on the acceleration, and if acceleration is equal to g, you are in free fall. Or when you are in free fall, means tension is 0, means your acceleration going to be equal to g. You can solve for that actually. So if you plug in t equal to 0 and solve this equation, you're going to get a equal to g. See, so that's the advantage of writing this way. So that's why in physics we write this way, okay, rather than just writing a number, because one equation can tell you several things. We're not doing math, we are doing physics. Physics comes from the math. Math is a tool, okay? So some number, some answer comes from the math, but when we write that in something like this, we can get out a lot of things from there, okay? So that's the reason behind it. So I want you guys to practice that, learn that little bit, okay? I'm not gonna be asking very complex algebra, but this, I expect you to do it, okay? So algebra worksheet is still there, posted. Answer is there. You practice it, see if you can get it, okay? If you still feeling uncomfortable. So that's why I emphasize so much at the beginning, folks. Okay, so now there is this little short video. Yes.
So you wrote AY at the beginning and then just wrote A. Are we supposed to write AY all throughout the equation, or just A is okay?
So AY is formula and A is acceleration in that particular situation here, just like we said, that's A.
Yeah, I got it. Thank you.
A is the value. In this case, it is 1.5, okay? But AY is acceleration, not just value. It has both magnitude and direction. So that's why there is negative A, not just A, but negative A in this case. Did you realize that? See, there is a little difference, although it may look exactly same. There is that little difference there, okay? So next slide has, oh, what happened? I'm going backward, oops. Okay, this has a little video here, okay? So this one came from one of the publisher of the book, and the person who is talking here is the writer of that book. And what book I'm talking about? The book I have listed as a reference book, okay? But it doesn't matter, just watch video and learn or see what you see here, okay?
We're in the elevator and we're moving. We're moving at a constant speed, acceleration 0, net force is 0, but now watch what happens. There was a small bump, and the bump corresponded with the elevator stopping its motion. And when that happened, there was a small increase in the reading on this dial. This went up to 23. Now we know the weight is 22, but the dial went up to 23. So that tells us something. Think about the forces that act. Spring force up, weight force down. For just a second, the spring force was bigger, okay? So I'm going to ask you this question. Right when we had that bump, when it went up to 23, was the elevator moving up or moving down?
Okay, so can you answer that kind of question from what we know, okay? So here is this question related to that. So what happens? What is our weight? How do we get our weight? We step on a balance, right? So we push balance, balance pushes us up, right? So we are standing on the balance. So yeah, unfortunately, I did not bring my scale here, but let's say this is scale and this is us or this ball. What's the weight of the ball? how balance gets the weight of the ball? Ball is pushing this balance down, and balance is reacting back with the normal force. Okay, so there is normal force from the balance. Okay, so that normal force and the weight, the pull from the gravitational pull, they are same if this is not accelerating, the system is not accelerating. But if it is accelerating, what happens? Just like we saw, tension becomes larger or smaller. When elevator is, you know, accelerating up or down, tension can be larger or smaller, and tension wasn't equal to mg, was it? It wasn't. Similarly, normal force can be larger or smaller than mg. So when you are in elevator, just like you saw that elevator, that thingy, the candy, I think those were candies, the weight of the candy changed a little bit when elevator was stopping, or yeah, I think the guy said it was stopping. So there was acceleration. So whenever there is acceleration, what happens? The weight is no longer equal to mg. That is called apparent weight. Okay, that is called apparent weight. And how do we calculate apparent weight? By finding the normal acting on that object. So when there is acceleration, normal is not equal to mg. If you are standing on the scale, normal force from the scale is not equal to mg if there is acceleration. Net force is not equal to 0, right? N minus mg is 0, net force is 0 only when acceleration is 0. When acceleration is 0, this is 0. But if acceleration, when acceleration is not 0, this is going to be what? It's going to be m times a. And is this going to be negative or positive? That depends on our choice of coordinates and whether it's going up or down. So that's how thing changes based on Newton's second law. And we saw in the elevator, the weight was briefly changing when the elevator was stopping, okay? So now here is this question for you. So this person is, let's say, standing on the elevator. So last time we talked about tension on the rope. Now we are talking about normal force on this person, not the tension, but the normal force, okay? So object of interest is not elevator anymore. Object of interest is person. So person has a weight, pull from the gravitational force down, and the elevator floor is pushing that person up now, okay? And that's the normal force. Now, here is this question for you, okay? After that, so here is this question. The apparent weight, which is this normal force, is it bigger than the weight when object is, it is bigger than the weight when object is doing what? Okay, so here are some choices. Oh, what happened here? So I'm going to open the poll. Do you guys see this class in your clicker thingy? So can you poll it?
Yes.
Okay, yes. Looks like it's working. For a moment, I thought it wasn't working. Okay. So you have a minute. Maybe you want to write down the equation with n, mg, and maybe acceleration or no acceleration. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what happened. Okay, so we are seeing all of these, but mostly C. So let's say I'm thinking C as the correct answer, let's say. I don't know if that's the correct or not, but I am thinking that is correct. So how do I come up with that conclusion? Can somebody explain that? Or if you think I'm not correct, tell me why I'm not, okay? I like to really like to hear from you guys, okay?
I got it from looking at the equation. If you look at the equation, there are 4 variables, and in this situation, 2 of the variables are mass and the actual weight, and those remain constant.
Can you read your equation?
Yeah, I have N minus mg equals ma, the apparent weight equation.
MA.
Yeah.
So that means we are assuming up as a positive?
Yes.
Okay. So mg is the weight. So in this case, N is mg plus ma.
Right.
So if acceleration is positive, that means normal gonna be larger than mg. Is that how you are looking at?
That's a way to look at it. I actually looked at it simply as you have the 4 factors, and of those 4 factors, the actual weight of the object and the object's mass are always going to be constant. Mm-hmm. So the apparent weight and the acceleration are going to be related.
Right.
And as your acceleration goes up, then your apparent weight is also going to go up.
Okay, yeah, that's the one way to look at it. Yes. Yeah, that's really nice. Okay. Or we can also write something like this. And if A is positive, we can tell N is bigger than mg. So for example, if mg is 100 and m is, let's say, 10, and A is positive 1, then normal gonna be 110, right? Yes, you don't need all these numbers. You can see normal gonna be 110 when A is positive. But if A is negative, let's say, if it was going down, accelerating down, if that was negative, then this would be 100 minus 10 means it would be 90, which is less than the weight, mg, which is 100, I'm assuming at this point. Yeah. Okay, so looks like, yeah, C is the correct answer in this case. So the weight remains same, but the apparent weight changes when there is acceleration. Okay. So weight changes only if g changes. So that means if we go away from the earth, then weight may change. Okay. But as long as we are near the earth, as long as g is fixed, then what happens? mg is fixed, but the normal force can be different. So apparent weight is different. So for example, if the elevator were to be freely falling, then what's going to happen? Acceleration going to be, so now falling means acceleration is negative. So your equation going to look like this. So where is it coming from? It's coming from, again, same equation, okay? MAY. So now, accelerating down. And I'm assuming up as a positive, so that's why normal force is positive in my equation, okay? So this would be negative. That means this equation would be now negative, just like we saw for the tension, right? Now, what happens if, or let's say when A is 0, sorry, not 0, but A is G, then N gonna be what? 0, right? When A is G, that means it's gonna be mg minus mg, means N gonna be 0. Normal force on you is 0, so that means floor is not pushing you. That means your apparent weight is 0. You don't feel any weight. You become weightless. So that's why the, astronauts, for example, the people who are orbiting around, let's say, International Space Station is orbiting around the Earth. But it is also falling down with it has acceleration equal to z, actually, okay? So it's in free fall. So because of that, all those astronauts in the International Space Station, they have acceleration equal to z. They are in free fall and they feel weightless. Okay, so that's what weightlessness means. Okay, so they are weightless because gravitational force is not, it's not because gravitational force is 0. They are weightless because their acceleration is equal to z at that point. They are in free fall. They are free fall, but they never reach to the Earth though. They are not dropping down, but they are moving sideways. So those things are going to be more clear when we talk about circular motion. But for now, let's keep that in mind, okay? So have you ever jumped off from the, let's say, table or something like that? Do you feel a little bit different for that moment? I don't know. That's going to be very short time. But Ferris wheel, the one that kind of rotates a bit faster, when your bucket is really near the top. Oh, I have a bucket here. Okay, so let's suppose you are sitting here. I don't have you, but let's say this here. You are sitting on this bucket, and bucket goes to the maximum height, and of course it's spinning. And bucket, what happens? It becomes inclined, and then suddenly it goes like this. For that moment, it's in free fall, or close to free fall. For that moment, when it goes from incline to straight down, when you are turning, okay, on that Ferris wheel from the highest point, you feel different. You may hear people screaming at that point. Why? Because we are used to mg. Now there we feel it's different from mg. So we feel different, and that's when the screaming occurs. Has anybody heard this scream? If it's really slow Ferris wheel, that just for the for the viewing from the height, it goes really slow. So there is no such thing. Okay, it doesn't happen like that. But if it's moving a bit faster, in that case, we notice that. Has anybody had that kind of experience or seen that?
Yes.
Okay, good to know that. Okay.
Yeah.
So,
Quick question, Dr. Dingana.
Yeah.
How does that apply to skydiving? Are you free falling the whole time?
Yeah, skydiving, you are falling, yes, your acceleration, you are not, at the beginning, let's say if your parachute is not open for the moment, you are nearly at the free fall. So you feel kind of weightless there too. Definitely less weight, okay? but it's going to be very close to free fall. Yes, when your parachute is not open yet. Is that what skydiving is?
Yes, it is. I was just asking because when I did it, it felt different from a roller coaster. So I was just wondering.
Right, yes. So if your thing is already open, you know, like if you have some sort of wing or let's say a parachute, if it's open from the beginning, it's not going to be that noticeable. But if you just jump and then open later, so before you open versus that initial jump, in between, you'll feel that very different, yes. And when you are falling down, as long as you are accelerating, you will feel that difference, but not as much though, okay? So it takes, you know, like getting used to it a bit, okay? Good to know that experience.
It would be like when you're in an airplane, Sheila just said it, and you hit an air pocket and you just drop.
Right, momentarily.
Yeah. My son, he loves aeronautics, and so when I fly with him, he always tells me when I freak out because I don't like it, don't worry, Mom, it's just gravity.
So it's now you tell him it's yes, free fall. It's called free fall nearly, or apparent weight, more specific, right? Now you can be that.
Yeah, that I finally know something more than my 12-year-old.
Okay, so now here is question for you guys, and notice it says be constant. Okay, you have a minute to answer this. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Oh, we got varieties here. It's down. So shouldn't tension be less than weight? D. So let's suppose I am thinking D as the correct answer. Am I right or wrong? Why?
I think you'd be right, because if tension were zero, it'd be free fall, it'd be accelerating. If tension were equal to or any greater than the weight, then it would be holding its position.
So you think I'm right here by saying D?
Yeah.
Okay. But looks like a lot of folks don't agree. So why you think I'm not right, folks?
Well, I would think it would be B because it's saying that it's being lowered at constant speed, so that implies Newton's first law, so that means that there shouldn't be any net force, so tension and weight should be equal to each other.
Oh man, you have to think all those things? So does that make sense, folks?
I agreed with the reasoning for that D is correct, but I picked B because I didn't have enough time to do the equation before we ran out of like polling.
Oh, that's not so nice. I should be giving a bit more time then, right? So tension is there, W is there. How about acceleration? constant velocity means zero acceleration. Is that right?
Yeah.
So sum of forces must be equal to mass times acceleration means it's a zero. So let's say up is positive. So T minus W is 0 means T is equal to W. Hey man, you are right. So that's what you are talking about? It sounded like that, yeah?
Yeah, that's exactly what I was.
Hey, you are smarter than I am. Thank you for being smart. Okay. Looks like B is correct answer. So when there is acceleration, tension may change, the normal force or the apparent weight may change, but when there is no acceleration, no such thing happens. Net force is still zero. Okay, so let's keep that in mind. Yes, it always confuses us, but now we are that warrior who is trying to fight with that confusion. And I'm showing you how to fight, but fight is yours. Okay. Anybody likes to contribute more on this? Something sounds fishy here. Let me know. Let's discuss. I'm pretty sure some of you thinking something sounds a little fishy here. I can hear that sound coming out from your head, but it's not very clear. Can you speak?
I'll say that, you know, I've been working with Carl in his SI sessions to really understand this concept of, you know, something can move with a constant velocity, but you have to think about it in terms of Newton's laws. If there's no net force, then it would be the first law, they would be equal. Even though it's moving, it's in inertia. So initially, you know, I hit A first, and then I remembered what Carl had been working with me on, and that idea of does it have a net force? Does it not have a net force? And then are they individual forces? So that's where I'm still understanding those reasonings at that level.
Yeah, that sounds wonderful. And I can tell Carl is doing a wonderful job here.
Thank you, Doctor.
Yes, he is.
Okay, thank you, Carl. And thank you, Sayla, for sharing that, okay?
Thank you so much. Thank you. That means a lot. And Silas also is coming to SI, and it shows. So please, anyone who is confused, please come to SI, because we are doing fun things and learning a lot.
So now let's move to friction. So we already talked about friction, but what happens is sometimes we may not be given the friction force. Rather, we may be given some property of the surface, what we call friction coefficient, okay? So if that's given, how do we handle it, okay? And where does the friction actually arise from? Let's talk about that briefly, okay? So what happens is, let's say there is this table. When I push this table a little bit, unfortunately you cannot see it, I'm pushing it, right? What happens? I'm applying force. But this is not accelerating, not moving. So initial velocity is 0 and final velocity is still 0. That means there is no acceleration. So what's happening to the force I'm applying? What's happening to that force?
Is it equal to the one the table is giving back?
Right. So what's happening is now the table is applying with the same force, but at the same time, the ground is also feeling that force, and ground is applying force on the table, equal amount. See, table is trying to move, but it's not moving. Why? Because it's trying to move, means it's pushing the ground. So when you are moving, what are you doing? If you like, you can take 30 seconds, just get up and walk. And what your feet are doing, you know, when you are walking, is it pushing the, let's say, carpet or surface? Is it pushing it? You pushing the carpet, your feet, and is the surface pushing you back? So what would happen if there was ice and you are trying to walk? Why is different to why it is difficult to walk on the ice? Do you want to walk a little bit? Stretch your feet. I'm waiting 30 seconds here. Feel free.
Yeah, I gotcha. Why is it hard to work on ice?
Mm-hmm.
It's hard to work on ice because you don't have any friction on your shoes, and you have a tendency to slip and slide everywhere because it takes much less force in order to cause you to accelerate in one direction that you really don't want to.
Right. So how does walking occur? We push the ground and ground pushes us back, right? But if there is no friction, ground cannot push us back like that. So we trying to move in horizontal direction, so that means we are pushing ground in opposite of that, you know, the direction we are trying to move. And ground should push us in the direction we are trying to move, right? So in that case, what happens? When we are trying to move, we are not pushing ground straight down, are we? We're not. We are pushing ground sideways. Did you notice that when you walk? Okay, you can try that. We are trying to push. We are pushing ground sideways a little bit. Okay, they're going to be component, horizontal component, because we push little inclined. Our feet, you know, our foot becomes inclined. One foot becomes inclined when we are taking a step. So what happens? The ground has to push it back, but what happens is we cannot push the ground if there is friction. We slip, our foot slips, right? So there is a lot less force or no force at all, just like we heard from Robert, okay? So there can be friction even when things not moving. So you push table. If table is not sliding, what's happening is that force is being neutralized, balanced. That's the friction force when object is not moving, and it's called static friction force. Okay, so you apply force on something, and that object applies force on the surface. For example, here, the surface, I am pushing one of my palm with another one. Okay, so that's the applied force. Now what happens is another one is opposing it. So another one is opposing it. So if I just apply a little force, then my palm not gonna slide over another one. Okay, so when applied force is 0, if I'm not pushing it, it's not gonna be up, pushing me back. Of course, I can try that, sliding my hand palm on the table. I can do that, okay? And I invite you guys to do that wherever you have. If you have table, you can try that table, on the bed, or on the wall, okay? If you're not trying to slide it, you don't feel any force. When you try to slide it slowly, you feel that opposing force, and it increases as your push increases, okay? So if I were to draw a graph, this is how it looks like. You apply force. If it increases, what happens? The opposing force is increasing. So they are one by one, equal and opposite. It's like the action and reaction there, okay? Applied force is equal to friction force. Now, what happens? After certain maximum value, things start sliding. So for example, your hand may be sliding over the table after you apply so much force. So once it starts sliding, we call that kinetic friction force. So before it slides, what happens? Static becomes maximum. That's what we call maximum static friction force. And it's important because we can tell how much is it just by knowing the nature of the surface. What kind of surface it is. If we know that, we can calculate what would be the maximum friction force. See, the friction force, static friction force is equal to applied force. But when it is maximum, right before it starts sliding or just barely sliding, that's when it's maximum, okay? And that maximum value is given by this equation. It depends on normal force, and you already know what normal force is. Normal force is related to weight. It's not always equal to the weight, but it is related to weight, okay? Sometimes it is equal, sometimes it's not. And there is this thing called static friction coefficient, okay? And this can be measured by doing an experiment, and you can find the value. So for example, what's the mu s for the wood on wood? You can find that, okay? What's the mu s for the wood on the metal surface, let's say, iron? Somebody has already done experiment and found the value, and it's listed. You can search for it. Many of them you can find in your book, okay? So what that means, so if we know the surface, you know the mu s, and if we can find n, which we should be able to find it, we'll see soon, that means we can calculate that value, okay, maximum. If it's not maximum, then you need to know how much you are applying. That's kind of tough, you need to measure. So if you are pushing on the table, how much are you applying? Getting that number gonna be a bit tough, okay? But the maximum value you can find. So that's why it turns out handy. So now once the object starts sliding, motion begins, then what happens is the value of friction force becomes smaller and it remains constant. And that we call kinetic friction, okay? That's what we call kinetic friction force. And it is given by the same equation, but now the friction coefficient is slightly different. What happens is, once the object starts sliding, the force becomes slightly smaller. As you can see, in this graph, maximum was somewhere here. If this was 12, then it is down here, maybe 10. See, it's smaller here. Now the friction becomes smaller, okay? And it does not depend on the applied force anymore, okay? So that's motion thingy, and it's fixed, it's not increasing. Maximum value is also fixed. It's given by that equation. This thing is fixed, and it is also given by very similar equation, okay? Only difference is this friction coefficient. So you can measure those things and you can find those listed. So for you, maybe if this is given, you can calculate this, or if you can use this equation depending on which friction force is given, okay? You can calculate mu k, or if mu k is given, then you can find friction force. So often in the problem, you may be given either this coefficient or this coefficient, or you're going to be told what surface is. If you are told surface, you can look for the value. If the number is given, you can use that number, okay, and calculate friction force. So friction force and friction coefficient, they are related, but they are not same. Friction force is friction, it's a force. Friction coefficient is not a force. It's just a fractional number. When we multiply that number by a normal force, that's when it becomes friction force. So often what happens, we, as a student, we tend to not differentiate between friction coefficient and friction force. In the problem, you may be given friction coefficient, and you may be using that as a friction force in the equation. Not good. That's a mistake, right? So if friction force is given, it's going to be given in terms of Newton unit, because unit of force is Newton. But if friction coefficient is given, you won't see any unit, because if I rewrite this, mu k is Fk over N. Both of them are force. They have same unit. So when we write, let's say Newton here, it cancels. The unit cancels. So it's a unitless number, okay? So that's one way to easily figure out whether it's a friction coefficient or friction force. And once you figure out it's a friction coefficient, how do you find friction force? How do you find friction force from friction coefficient, folks? Given friction coefficient, how do you find friction force?
Multiplied by the normal force.
Normal force, that's right. So normal force can be equal to mg or different. Keep that in mind. So to figure that normal force out, you need to make free body diagram and use Newton's law. Okay, remember, when something is accelerating, normal force cannot be equal to mg. That happens. And there can be other situation. You cannot tell for sure unless you draw a free body diagram. So don't try to skip that portion of drawing free body diagram when you are playing with the force, when you are working with the force, okay? Whew, I'm talking too much. So basically friction force comes from this microscopic, bonding. If you have taken chemistry class, probably you guys know the bonding. There are bonds, ionic bond, covalent bonds, right? So essentially it arises from there, okay? And so when something is trying to slide over another thing, it's pulling that bond, it's stretching that. It's like it's stretching a spring, okay? And so that's where this force comes from eventually, okay? So that's about the friction. So let's take a break, and then we're gonna talk more about it, how we solve problem related to this, okay?
Dr. Ramesh, quick question about the exam. You said that if we're doing it on our laptop, we can show you our desk before we start?
Yes.
As a heads up, oh no, all of our connections unstable. Oh no.
Well, I'm at the office. I've been having nothing but network issues today, so I thought it was just me. I feel better.
I don't know, it could be me. It just kicked me out for a moment, right? I don't know what that means.
Yeah, we're all experiencing internet outages throughout the region, and Zoom is having issues. So, yay! So hopefully it'll be back and done soon. We can only hope. We can only hope. Ah, hack attack.
Record. Yeah, looks like now it's recording, right? Yes. Okay. So for the record, if there is no applied force, there is no friction. And applied force is equal to, friction force is equal to applied force, as long as object is not moving. Okay, object is not sliding, that means it's equal. It's like a reaction force for the applied force. So applied force, think about applied force as an action and friction as the reaction of that, static friction. Okay. Okay, so now let's move on and let's learn how to use friction to solve problem. Okay. So there is this block on the floor, right? And there is horizontal force like push force on the block, right? So let's say there is this block. So its mass M means, so free body diagram of the block I'm drawing, okay? Block, and this is free body diagram. So it's on the surface, horizontal floor means weight gonna be down, normal force gonna be up. So that's that. And there is this horizontal force, push force, let's F, just like we talked about, okay? But what it says, it just starts to move. What that means, it's not already moving, it just starts to move. That's a key word for maximum static force.
Dr. Dungana?
Yes.
If it doesn't specifically tell you the direction it's moving, but it tell the force that it's telling you is positive, like 12 newtons, do we just assume that it's going to the right?
Oh, you can assume that as a left as well. It doesn't matter. So we are kind of used to drawing like that, right? But it does not have to be. So let's say this. Let's do this. Still equally valid. Okay?
Okay.
Let's do that. And that's gonna also tell us that friction is not always negative. So let's say I'm assuming this as a positive. Okay? This as a positive X. So now friction force is positive, and applied force is negative. So this positive and negative, that simply depends on your choice of coordinate. And while drawing it, you are free to draw any direction you like, unless you are asked to draw the way, you know, a particular way, because the answer going to depend sometimes the way you are asked to draw, okay? But if it's not asking you, shouldn't matter. And final answer shouldn't depend on your choice of the positive x-axis. I'm glad you asked. Okay, so let's do that. So what is the coefficient of static friction? So in this case, it's asking us in part A, mu s is what? Coefficient of static friction means mu s is what? It's not asking for friction force, it's asking for that. But we know mu s and Fs max depends on like this, right? So that means mu s gonna be Fs max over normal force. Oh, hold on. So in free body diagram, I wrote normal force as a lowercase n. Here I'm writing uppercase N. I'm pretty sure I'm confusing you guys. What should I do? Should I use lowercase or uppercase?
Should be lowercase because we're talking about the normal force and not newtons.
Okay, so let me replace that. Yes, in some places in my slide, there are uppercase N, okay? I'm sorry about that. So that's that. So now, Fs max, how much is Fs max? How much is normal force? Do we know them or can we find them? So for that, we need to look at the free body diagram. Okay, so if I look at the free body diagram, what do I find? Fs max is same as the applied force. Their value, they are same. Of course, the direction is opposite, right? The value is same. So here, I'm just looking for the values here, okay? So what is the value of Fs max, which is same as F? So I can just write in place of Fs max, I can write F because this. Or if you like, you can say Fx must be 0. That means Fs max is equal to, oh sorry, Fx max minus F equal to 0 means Fs max is F, right? So
I
that's
have a
the
question.
Yes.
Why is the net force 0 if the object is just starting to move? Wouldn't it have a net force then? Or is it because it's just starting to move, so we're thinking the instant before it moves?
Yeah, it's the second choice you are talking about, okay? So since there is no such, you know, another right word to explain it, usually that's how it is done, okay? So it's not really moving, but we know it's about to move. So the friction force has become, I mean, static friction force has become maximum. That's the key word. That's what this is, okay? Keyword for that. What you said, the second choice, okay? Yeah,
Okay,
I'm
thank
glad.
you.
I'm glad you, you know, confirmed it. Yes.
And Professor, why wouldn't it be a negative F? Is it because it's just the same value? It doesn't have to do with direction?
Yeah, so if I look at this equation, I'm now here in this equation, okay? So what happens? Fs max, value of Fs max is equal to F, not negative F, right? Oh, we are losing somebody. Okay, so Looks like, I don't know if that was the noise from outside, not actually person trying to ask question. So let's move on. So in this case, we are just looking at the values. Direction is shown by drawing the arrows, okay? The arrows means direction, but the value, so for example, if this is 10 Newton, this is 10 Newton. So this is 10 Newton to the left, this is 10 Newton to the right. But what's the value? 10 Newton. So that 10 Newton I'm writing here by writing just F, okay? And when we write equation properly, net force is equal to 0. See, I'm writing one as a positive, another one as a negative. And eventually when I solve this equation, I get Fs max is equal to F. I'm getting value. The direction, I took care of that by writing negative sign here. So sometimes when you have balanced force like this, it's easy to just look at, oh, this is being balanced by this, so the values must be same. And you can just replace one by another one. That's the shortcut way of doing it. Long way, this. Do this, and so, oh, Fs max is same as F. So now let me plug that in there, okay? So that's the systematic way of doing it. But we can just look at the free body diagram when we draw nicely, and we can tell Fs max here is balancing F, means those two forces must be same. Similarly, normal force is balancing weight. So in this case, normal force is equal to weight. So that's the mg. So now with this, I know everything, okay? Value of F is 12 Newton. Oh, F was right there, 12. Why did I write 10? Okay, so 12 Newton, and M is 3 kilogram, and G is 9.8 meter over second square. So when you get, you know, once we take the ratio, we're gonna get this answer here, okay? So that's 0.41 we should be getting. So now let's look at part B. So it says a 7 kilogram block is stacked on top of 3 kilogram. What magnitude of F, the force acting horizontally on the 3 kilogram block before that is required to make the two blocks start to move? So just to make it start, what new force should be, you know, we need to apply. Now that applied force 12 Newton not going to be enough because there is more mass. More mass means more weight. More weight means more normal force. More normal force means larger friction force. So how this is going to change? Now let's say, now I have a new free body diagram, but it's going to look exactly same. So if you like, you can change the n as a n prime, or you can just leave it n, okay? And this one gonna be uppercase M times G, where M is now, since one is sitting on top of another one, what happens? It's like 3 plus 7. Okay, so that means it's gonna be 10 kilogram. Okay, so that's going to be just 10 kilogram, and everything else is going to be now same. So let's say Fs max. Let's forget about the prime. Otherwise, we have to put prime in every one of these. So let's assume these things are now new for part B. Okay, so now F, we want F in this case. F is what? So for this surface in contact, they are still same. Same block, same horizontal surface, they are in contact. That means mu s is still same. Okay. Oh, you guys are chatting a lot. So mu s is still same. How much? That's 0.41 from A, because it's the same surface in the block. Okay. So that means basically now part B is same as A. So let me quickly erase this and write that, since I'm running out of, actually I already passed our regular class time. Sorry about that, folks. So since we are interested in this, let's write down this. Sum of forces along the x direction must be 0. So Fs max, just like before, Fx max minus F must be equal to 0. So now, what is F then? F is equal to Fs max. I just, switch the side of both of these, let's say. Okay, so now what is Fs max? It's mu s times normal, but what is normal force this time? Mu s times N is uppercase M times G from the free body diagram, you can see. So where M is now 10 kilogram. So that's how it changes. So now you can calculate that number, and that's going to be around 40 Newton, I think. I don't know if I rounded it correctly or not. I don't quite remember. Okay, folks. Again, sorry for going a little over the class time. We had some disturbances. So I'll see you guys next week, but I'm still here. If you want to ask some question or talk something, feel free to do it.
Thank you, Professor Dungana. I hope you have a lovely day.
You too. I'll see you next class.
Professor Dungana, will our gravity in this problem be negative 9.8?
G is always 9.8.
Okay, thank you.
Never negative when we write like mg, okay? Acceleration, when we write like ay, acceleration, that can be negative or positive, okay? G is just the symbol for this number 9.8.
Thank you.
Okay.
This was a great class. Thank you, Dr. Dungana.
Oh, thank you very much.
You have a great weekend, and I will see you on Monday.
See you.
Thank you.
Thank you.
Dr. Dungana.
Yes.
Thank you.
I know this may not be necessarily the case every time, but in this particular example, if you see that the difference between part B and part A is simply a change in mass, can you just use the final equation you ended up with part A, where mu s equals F over mg, and just plug in the new variables?
Yeah, if you can understand what's going on, yeah, you can do that, yes.
Okay, all right, thank you very much. Have a great weekend.
Oh, you too.